Okay, welcome. Thank you for being with me here. I'm going to try to explain everything you need to know in the Thevenin Equivalent Circuit in, I don't know, let's go 10 minutes or less. So, the first thing you need to know is my name is Austin Rafus. I am an electrical engineering student here at Liberty University, and that's all about me. So, the Thevenin Equivalent Circuit, what's it used for? What does it do? Why do I need to know? Well, it's actually a really useful theorem. What it does is it takes a circuit like this that looks big and kind of scary, and you shrink it down to a circuit that looks like this. Hopefully you guys can see that in there. Let me check. Yes, you can. So, we shrink this guy down to this. Very handy, very useful. So then we can work with this guy here instead of this guy because this is equivalent to that. Awesome, right? Okay. So how do you do that? Because I'm sure that's what you're here for. So the first things first, we have our values right there. Let me make sure you can see that again. Yes, you can. Okay. So the first thing we're going to do is we're going to get rid of our voltage source. Just like that. Why? Because we can do that. If you guys haven't noticed yet, I have a colorful setup here. What I'm trying to do with that is make things easier for you to see in the video and to help you understand where everything is. So let's just run through the colors. The blue is voltage sources and general circuit drawing. So we have our VS in blue and our voltage drawing. Green is going to be our currents, and black is our resistors. So let's go through what we actually have going on in the circuit right now before I jump into reducing. We have VS, which is our voltage source. We have our resistors R1 through 6. Their values are listed here. And then we have 3 currents and 3 nodes. So it doesn't matter what you pick here to analyze the circuit, voltage or nodal, because we have the same amount of nodes and meshes. But because we have a voltage source, I think I'm going to choose mesh analysis later on in the video. So, first things first, we turned this off. So now what does that do? How does that circuit look? Let me draw that as you guys are bored out of your minds. One thing that if I can share some wisdom with you, I found when it comes to drawing resistors is that go 3 peaks up, 3 peaks down, and you'll get the perfect ones. Okay, but you say, Austin, there's 7 resistors, to which I agree with you. But if you look here, we have one at the very end called RL. RL is our load resistor, and for this part we're going to get rid of it because it has no value. That's something kind of separate. And so this is what we have now. This is what our circuit looks like before I put anything else in. So let me put in other things and you guys can see the similarities. Okay, I'm sorry for crossing in and out of the video. Here's what it looks like now. So R1 flipped down to be in parallel with R2, which if you're to this point, you know makes sense. And we're just going to be working with this right here. So I'm going to only take you through 2 examples, and then we're going to flash forward in time a little bit. So we have R1 in parallel, that's the symbol for parallel if you didn't know, in parallel with R2. Okay, and we're going to set that equal to RE, our R equivalent, our resistor equivalent. That's going to eventually turn into our R Thevenin. But for right now, it's just equivalent as we're working through the circuit. And so, what does parallel mean? So RE, so our resistor equivalent, is equal to R1 times R2 over R1 plus R2. So that's equal to, and we're going to look here, 40K ohms, so 40,000 ohms, times 40,000 ohms over 40K ohms plus 40K ohms. Now, if you guys aren't good at adding resistors, that's a pretty good review of how to do it in parallel. And I'll show you series in just 1 second, but go and practice that. If you're not good at mesh or nodal analysis, go practice that. It is imperative you know it. So RE is equal to 20K. So how do I know that right off the bat? Well, there's actually a little bit of a trick here I learned the other day and thought was really cool, and I'm going to prove it to you now. So we have 160K, and you can almost picture it, and for this illustration I'm going to put a 2 up above the K. There's no squaring going on, but just picture it like that with me for a second. Over 80K. And so that squared cancels out with that K. So now we have 160K over 80 equals to 20K ohms. Just a neat little trick. I didn't know it. If you have the same resistor values in parallel, they'll come out to be half of what it is. I just proved it to you here. Pretty awesome. Hopefully that'll save you guys a little bit of time in the future. So now what happens? Now we're going to redraw the circuit again. I'm sorry, my drawing is not the greatest right now, but if you see what I'm trying to do here, you can see I have my peak, so let me relabel this guy and then you'll see where we're at. So now we're going to introduce our RE, our equivalent resistance value. Very exciting, it's the first time we're using it as a placeholder. This guy is R3, this guy is R4, R5, and R6. And who are we working with this time? Just the last two again. So cool. And I'm crossing over again. So now what are we going to do? Well, it's in series, so RE in series with R3. So all that is RE plus R3. And so that's 20K ohms plus, and our value over here tells us R3 is equal to 10K ohms. And so RE, because this is going to move with us, guys, don't get confused by that. RE is moving with us. Is going to turn into 30K ohms for this next iteration. And so I'm going to zoom in on this so you guys can see it. And then I'm going to flash us forward. So there you go, guys. All right. This is bad cinematography, I apologize. Okay, so flashing us forward in time now. This is the rest of it. I'm going to zoom you in on that. There you go. You can pause it. All I do here is I keep going with the process, parallel, combine them, series, combine them. And finally we get to RE and RE number 6. So we went all the way from here, all the way to this guy right here. And then, very simple again, if you didn't catch it the first time, two values are the same, in parallel, flip it, half it, 10K ohms, and then, as you can see in red, we found something we needed, which was RTH. So that's pretty awesome. Okay. So now, we have something else we need to do. Let me make sure I'm zoomed out so you can see me again. There we go. Okay. So as you can see, we're getting close. Now what we have to do is we have to set up our equations for our mesh analysis. So these are pretty easy. We have I1, I2, and I3, all of which are unknowns. And so that means we're going to need three equations, three unknowns, not a problem. Okay. So we have -10, because that's the way our current is flowing into that voltage source. Plus, it's going to hit the positive side of that resistor first. So it's going to be plus 20K I1 plus 20K. And when I say K, I'm referring to the values of the resistors. So that could be 20K ohms just as easily, and that's going to be I1 minus I2. That comes from these two currents over here intersecting. When I pull over and flash us forward in time a little bit more, you're going to understand better. I have a better diagram, and that's going to equal to 0, and we're going to call that guy E1. So then we're going to bump it so it looks a little bit better. 20K I1 plus 20K times I1 minus I2 is equal to 10. Awesome, because we have our voltage source. So the next one that's going to happen is 20K. So this is now E2. And again, green is for current, black is for resistors, blue is for voltage, and drawing the diagram. And red is what we're looking for the very end. 20K times I2, because now we're on I2's current, so it's I2 minus I1 plus, let's see what R3 is. R3 is 10. So 10K I2, and then plus 6K I2 minus I3 equals to 0. So if we're going to do anything here, we're going to leave this guy alone because he doesn't really have anything easy to simplify yet. So then E3, and this is the final guy we're looking for here, our third equation, is going to be 6K I3 minus I2 plus, let me look at my notes, I'm sorry, plus 15Ki3 plus 20Ki3 equals to 0. So we're going to simplify him down. So we have 6Ki3 minus 6Ki2 plus 15Ki3 plus 20Ki3 equals to 0. If we combine all of our like terms, we end up with 41I3 minus 6Ki2 equal to 0. So now I'm going to do the same thing I did before, and I'm going to wheel in one of the whiteboards I pre-prepared for you guys to save us some time, because I'm sure you don't want to waste your time doing this, and I don't want to waste your time. So here, like I was saying, our mesh currents there, they look a lot nicer on this board. And I'm going to step out, and you can look at that. We saw all the way down. And I'm going to zoom in. Awesome. But as you see, we only solved 2 of the equations here. We still have one more to solve, so I'm going to flip the board around, and you guys can now see we get I3's current solved for. So we go all the way across from VS to I3, and we make sure that we have that. So there you guys go. We'll make that nice and easy. Okay. So now we have everything we need. We have I3's current, and we have R6's value. Why is that important? And we have RTH. Well, we're going to solve for VTH. So let me make sure you guys can see what I'm about to do here. So let's go over what I've hit so far, where we're at and what we're looking for. We have RTH, we have RL, we need VTH or ITH. We can solve for VTH right now, so that's what we're going to do. So we have our I3 value, which is equal to 1.59 microvolts, which makes sense if you were paying attention as we come over. So the whole series was just voltage dividers across. So that should be a small current. And I'm sorry, not microvolts, microamps. I apologize. Times 20K ohms. And so these guys cancel out, and we end up with VTH is equal to 0.318 millivolts. Okay, so now the last part of the puzzle is, what is ITH? Well, the answer to that is you give me a value of RL, I can combine it in series with RTH, and then I can divide VTH by this new RTH, and I can give you ITH. So that's how you do it, that's what it's for. I used an example I thought and hope will be helpful for you guys. Thank you for watching. Thank you for the opportunity to do this. I will see you at the next time.